Yes, the National Electrical Code, or NEC, allows for the installation of a secondary grounding conductor from a grounding electrode to the ground bus in the back of an electronic test station, provided certain conditions are met. These conditions are: firstly, the grounding electrode must be part of the grounding electrode system. Secondly, the supply cord feeding the test station must have an equipment grounding conductor installed and properly connected. And thirdly, the secondary grounding conductor must be sized and installed in accordance with NEC requirements. The secondary grounding conductor must be insulated, using either copper or aluminum. The conductor must be sized according to Table 250.122 of the NEC. The installation of the conductor needs to be in a raceway, cable tray, or another approved method. Finally, the conductor needs to be protected from physical damage. The size of the secondary grounding conductor depends on the size of the overcurrent device protecting the circuit to which the test station is connected. The minimum size allowed is number 14 American wire gauge, OG. There are no length limitations specified in the NEC for secondary grounding conductors. However, it is good practice to keep the length as short as possible to minimize resistance. Concerns about fault current not finding its way back to the overcurrent device are valid. If the path through the secondary grounding conductor is not low enough in resistance, the fault current may not be sufficient to trip the overcurrent device. To mitigate this concern, the following steps should be taken. Firstly, use a low resistance conductor for the secondary grounding, for example, number 10 AWG or larger. Secondly, keep the secondary grounding conductor as short as possible. Thirdly, ensure that all connections are tight and free of corrosion. And fourthly, consider installing a ground fault circuit interrupter, or GFCI, on the circuit to which the test station is connected. The customer's requirement for an earth ground should be carefully evaluated to determine if it is necessary. If an earth ground is required, it should be installed separately from the secondary grounding conductor. If the test station is located in a hazardous classified location, additional requirements may apply. Now, let's delve deeper into the specifics of grounding and bonding, particularly as they relate to electronic test equipment and sensitive installations where noise and fault current paths are critical considerations. Grounding and bonding are fundamental concepts in electrical safety and electromagnetic compatibility, or EMC. Their primary purpose is to provide a low impedance path for fault current to return to the source, thereby facilitating the operation of overcurrent protection devices like circuit breakers or fuses. Additionally, proper grounding helps to minimize electrical noise and voltage differences between conductive parts, ensuring the safe and reliable operation of electronic equipment. The NEC provides comprehensive guidelines for grounding and bonding, and compliance with these guidelines is essential for ensuring electrical safety and preventing equipment damage. The grounding electrode system serves as the reference point for the entire electrical system. It typically consists of one or more grounding electrodes, such as ground rods, ground plates, or metal water pipes that are in direct contact with the earth. The grounding electrode system must be bonded together to form a single, integrated system with low impedance to ground. This ensures that all grounded parts of the electrical system are at approximately the same potential, minimizing the risk of electric shock and equipment damage. The equipment grounding conductor, or EG, is a critical component of the grounding system. It provides a low impedance path for fault current to return to the source, allowing overcurrent protection devices to quickly and effectively clear faults. The EGC must be sized in accordance with NEC Table 250.122, based on the rating of the overcurrent protective device in the circuit. It must be installed in the same raceway or cable as the circuit conductors. In the case of electronic test stations, which often involve sensitive electronic equipment, additional grounding measures may be necessary to minimize electrical noise and ensure accurate measurements. The secondary grounding conductor, also known as a supplemental grounding conductor, is often used to provide a direct connection between the equipment chassis and the grounding electrode system. This can help to reduce voltage differences between the equipment and ground, minimizing the risk of noise and interference. When installing a secondary grounding conductor, it is important to follow the NEC guidelines for sizing and installation. The conductor must be insulated and sized according to NEC Table 250.122 based on the rating of the overcurrent protective device in the circuit. It must be installed in a raceway or cable tray and protected from physical damage. The length of the secondary grounding conductor should be kept as short as possible to minimize impedance and ensure effective grounding. In some cases, the customer may require an earth ground for their electronic test equipment. An earth ground is a direct connection to the earth, typically through a ground rod or ground plate. The purpose of an earth ground is to provide a reference point for the equipment and to minimize voltage differences between the equipment and ground. If an earth ground is required, it should be installed separately from the secondary grounding conductor. This is to avoid creating a ground loop, which can cause noise and interference. The earth ground should be connected to the equipment chassis through a dedicated grounding conductor. Ground loops occur when there are multiple paths to ground, creating a circulating current that can introduce noise and interference into the electronic equipment. To avoid ground loops, it is important to ensure that there is only one path to ground for each piece of equipment. This can be achieved by using a single-point grounding system where all equipment is connected to a common ground point. Another important consideration is the type of grounding conductor used. Copper conductors are generally preferred for grounding applications because they have low resistance and excellent conductivity. However, aluminum conductors may be used if they are properly sized and installed. The grounding conductor must be protected from corrosion, as corrosion can increase resistance and reduce the effectiveness of the grounding system. In addition to grounding, bonding is also an important aspect of electrical safety and EMC. Bonding is the process of connecting all metal parts of the electrical system together to form a continuous, low-impedance path. This ensures that all metal parts are at approximately the same potential, minimizing the risk of electric shock and equipment damage. Bonding is particularly important in areas where there is a risk of flammable gases or vapors, as it can help to prevent sparks that could ignite the gases. The NEC provides detailed requirements for bonding, including the size and type of bonding conductors, as well as the methods for making bonding connections. All bonding connections must be tight and free of corrosion to ensure a reliable electrical connection. When working with electronic test equipment, it is important to be aware of the potential for electrostatic discharge, or ESD. ESD is the sudden flow of electricity between two objects with different electrical potentials. ESD can damage sensitive electronic components and cause equipment malfunction. To prevent ESD, it is important to take precautions such as wearing ESD-safe clothing, using ESD-safe workstations, and handling electronic components with care. In hazardous classified locations, additional grounding and bonding requirements may apply. Hazardous classified locations are areas where there is a risk of fire or explosion due to the presence of flammable gases, vapors, or dusts. The NEC provides specific requirements for electrical equipment and wiring in hazardous classified locations, including requirements for grounding and bonding. These requirements are designed to minimize the risk of ignition and explosion. When installing electrical equipment in a hazardous classified location, it is important to consult the NEC and follow all applicable requirements. This may include using explosion-proof enclosures, intrinsically safe circuits, and other specialized equipment. Regular inspection and maintenance of the grounding and bonding system are essential for ensuring continued electrical safety and reliable equipment operation. The grounding and bonding system should be inspected periodically for signs of corrosion, damage, or loose connections. Any problems should be corrected promptly to maintain the integrity of the system. Testing of the grounding and bonding system is also recommended to verify that it is functioning properly. This can be done using a ground resistance tester or other specialized equipment. The results of the testing should be documented and kept on file for future reference. In summary, grounding and bonding are critical aspects of electrical safety and electromagnetic compatibility. Proper grounding and bonding help to minimize the risk of electric shock, equipment damage, and electrical noise. When installing electrical equipment, It is important to follow the NEC guidelines for grounding and bonding and to take precautions to prevent ESD. Regular inspection and maintenance of the grounding and bonding system are essential for ensuring continued electrical safety and reliable equipment operation. Always consult with a qualified electrician or electrical engineer for specific guidance on grounding and bonding requirements for your particular application. Furthermore, consider the specific needs of the electronic test equipment being used. Some equipment may require specialized grounding techniques to minimize noise and ensure accurate measurements. Consult the equipment manufacturer's recommendations for specific grounding requirements. Also, remember that the NEC is a minimum standard. In some cases, it may be necessary to exceed the NEC requirements to achieve the desired level of electrical safety and performance. For example, you may choose to use larger grounding conductors or install additional grounding electrodes to further reduce impedance and minimize noise. The key is to carefully evaluate the specific needs of the application and to design a grounding and bonding system that meets those needs. Consider the potential for future expansion or changes to the electrical system. It is often easier and more cost-effective to install a robust grounding and bonding system upfront and to try to upgrade it later. Also, be aware that grounding and bonding requirements may vary depending on the local electrical codes and regulations. Consult with the local authorities to ensure compliance with all applicable requirements. Finally, remember that electrical safety is everyone's responsibility. If you are not qualified to perform electrical work, it is important to hire a qualified electrician to do the job. Never attempt to work on electrical equipment without proper training and safety precautions. By following these guidelines, you can help to ensure the safety and reliability of your electrical system and protect yourself and others from electrical hazards.